Good evening, everyone. My name is Shayok. I'm an assistant professor in computer science at Florida State University. And the title of my paper is Distributed Active Learning for Image Recognition. We all live in a world of big data. We are surrounded by actuators and sensors of different forms, which give us an enormous amount of data on a regular basis. Machine learning, as we all know, is used to organize and categorize the data, make sense out of unstructured data, and most importantly, give future predictions from past observations. To train a reliable machine learning model, we need a lot of labeled data in the form of a training set. Typically, the data is hand-labeled by human experts. So getting a large amount of labeled data is an expensive process in terms of time and human labor. This has set the stage for research in the field of active learning. In an active learning setup, we are given a small amount of training data, as shown by the green samples here, and a large amount of unlabeled data, as shown by the red samples in this diagram. In every iteration, a batch of samples is identified by the algorithm and given to the human annotator, who labels them and puts them into the training set. This process is continued iteratively until some stopping criterion is satisfied. The fundamental idea in active learning is to select the most important unlabeled samples for manual annotation. So that way you can get a machine learning model with the least amount of human effort. In today's digital world, digital data volumes are increasing at a rate faster than the ability of individual computers to store them. So it is possible that the unlabeled data may be split across multiple computers with little or no communication among them. The goal of this research is to develop an active learning algorithm for this kind of a distributed setup. Our active learning batch selection criterion is based on uncertainty and diversity, where the uncertainty of an unlabeled sample is computed as the entropy of the posterior distribution, as shown in this equation. The diversity of an unlabeled sample is computed as its minimum distance from the already selected batch. The final objective function to be maximized is a weighted sum of the entropy and the diversity terms. And the final optimization problem to solve is to maximize this score SB subject to a cardinality constraint on B. This function happens to have two very important properties. It's submodular as well as monotonic. And we use these properties to find a solution. To solve this optimization problem in the distributed setup, we use the greedy algorithm proposed by Mirza Soleiman et al. In NIPS 2013. The core idea is to run the standard greedy algorithm locally in each machine to select K samples. The samples selected across the M partitions are then combined and discharged to a backend server. And finally, the K samples are selected from this group of MK using the standard greedy algorithm. This simple yet efficient solution provides a strong mathematical guarantee on the solution quality with respect to the optimal centralized solution, as is formalized in this equation. Here are some sample results on two face recognition data sets. The horizontal axis denotes the size of the training set, and the vertical axis denotes the accuracy obtained on the test set. The goal is to study the increment in accuracy with increasing size of the training set. The black curve is the one obtained using R method, and we see that using R method, the accuracy grows at the fastest rate, which means the proposed method is able to identify the most informative samples from large amounts of unlabeled data in a distributed setup. This slide shows a comparative analysis of the distributed solution against the centralized solution. By centralized solution, we mean the solution that we would have got if we had the entire unlabeled data in a single computer, and if we were able to run the greedy algorithm in a single machine. We note that the two active learning curves are very close, which shows that the solution obtained by the distributed algorithm is very close to the centralized solution. If you want to know more details about this work, please stop by my poster during the poster session. Thank you very much.